Okay, hello. Welcome to Thermodynamics 3331. Today we're going to be doing Lecture 35, which is to start into cycles in Chapter 8 of the textbook. But first, I have a couple of announcements to make and just to answer some questions that I've been receiving from you all. So, with regards to the midterm exam, I know that you guys are eager to get those results back. I am still grading them. I'm almost through the third problem, and we'll attack the fourth problem, which many of you didn't have a chance to get to on the exam. So I should be able to wrap up the grading certainly by the end of the week, and you should have your grades. If you start to see grades appear on Canvas, those are not the curved grades. Those are just the grades that I'm going through. Those are the raw scores. So don't freak out if you see a raw score on the Canvas. We will correct those once I get a sense of the overall performance of the class and on the entire exam. Okay, so I guess my point is that we certainly are going to take the curve into account through the exam. Some people have asked me, well, since you made a mistake on the first problem, or the problem 2 with the first written out problem that that wasn't fair, essentially. And I agree with you, but except it's fair that everybody had the same information, because as soon as that question got brought up, I broadcasted to the class. So pretty much everybody was operating from the same disadvantage. And so from that perspective, it should be okay. I was very lenient in my grading, so I don't think there's going to be really much issue with that. Also very lenient on the second problem. Most people made up some ground in the second problem, luckily, and I think most people got that one. It certainly was the easiest of all the problems. In fact, I do want to spend a little bit, just a second, to go through my review problems. Somebody pointed out that here on problem, what is it? Problem 3. I'm sorry, I was just talking about problem 3. So the problem 3 is where people made up ground. This one here, the heat exchanger, because this pretty much was an exact copy of a homework or a problem that I did in class, a feed water heater. So this is like almost identical to that problem. So a lot of people did get this. And in fact, a lot of people pointed out my mistake down here. So if you look what's in red, I just changed that. So essentially I had the sign wrong in this situation here. Where I said the SDT equals 0 equals M.3S3, and like 4 or 5 of you pointed out that that was wrong. So that's good. At least I know that there's some people paying attention, that some people actually got this. A lot of people got these answers, so probably a good number of you I saw actually understand this problem pretty well. And then so what I did is I just went through and corrected this one. I'll repost this with the red, and then that way you can see it. It doesn't really affect many people's grades at all. In the end, it turns out that I meant for this to be sort of reversible, to essentially mean that this thing essentially equals 0, the entropy reduction. Some people got 0.00290050, so I gave credit for any of that stuff. So there isn't an exact answer that I was looking for, because it really depended a lot on what you got for this number, right? If you use 3 decimal places or 2, then it made a difference in the answer, right? So you could see it's reversible or not reversible depending on whether there was used enough significant figures. If you used enough significant figures, it would even come out to 0. So I had 0.00. Actually, if you do it this way, you end up getting negative 0.0007. It's essentially 0. I meant it to be a reversible process. So anyway, so it's a reversible process where that thing was supposed to be 0. The internal reversibilities were 0. Definitely mixing doesn't tend to be a reversible process, but it wasn't mixing of 2 different things. It was mixing of 2 different phases. So, excuse me. So it's possible for it to be reversible. Anyways, then most people got this. I gave a lot of leniency on this one as well when I was grading. So, most of you got the vapor dome. Some of you who didn't get the vapor dome, I of course couldn't do that. Some of you did exactly what I told you were going to do. You assumed this was an ideal gas, and for those people, I was a little unrelentless, because I've said so many times that if you're asking for quality, it's not an ideal gas, and you can't use constant specific heats. Okay, fourth problem I haven't gotten to yet. Most people didn't get through the fourth problem, but you have the solutions here, and I would recommend looking over them. I've given you a chance to to do another transient problem for homework. So hopefully that gives you a little more practice on this stuff. Okay. The good thing is you won't see transient problems again until maybe the final. Talking about the final, we have, including this video, we have 6 more videos left in the class, which is really scary to me because I had no idea that we were getting so close to the end of this lecture, to this class. The COVID-19 thing has really put a wrinkle in my plans to get through a lot of material in this class, and so we are behind, significantly behind what I'd like to be. So what we're going to do is we're going to cover chapter 8 and little bits of 9 and 10. So chapter 8 is about vapor power systems or vapor power cycles, and this is an important subject, which I'll explain here in a second. And we're going to get through gas power cycles, which topic that I just really love because that's something that I do in my research. And then we're going to get a little bit into refrigeration cycles, which are vapor refrigeration cycles, and that is really applicable to a lot of people who go into HVAC because that's what we're talking about. So I hope to end the class on a lecture on vapor refrigeration cycles, but really we're going to try to do two lectures on each. 2 lectures on Rankine cycle, which is the vapor power cycle, 2 lectures on gas power cycles, which is not enough. 0 Zippo, not enough. We're gonna have to pick a couple of my favorites. Maybe I'll do a lecture on each one of my favorites cycles, and then I'll have to leave you guys to study those other ones on your own. And then we'll do 2 on refrigeration cycles, and that will be the end of the class. So crazy times. Okay, so here we go. The other thing that I want to do, of course, is look at the chime in because I didn't go over these answers. So this was from lecture 33. Lecture 33. So we were talking about isentropic compressor efficiency and turbine efficiency. We're actually going to be going through this again when we do non-ideal cycles because they have compressors and turbines in them, and they're not usually, if they're not ideal, they have an efficiency associated with them. So the isentropic efficiency of a compressor is the reversible and adiabatic work divided by the actual work. Yay, most people got that. Some people got the inverse, which is this is the definition for isentropic efficiency of a turbine. Okay. This one, somebody just picked it. I don't know. It's really nonsensical. Heat out divided by the work. So this is actually, I was trying to make it seem like it was like the first law efficiency for a cycle, but we're not talking about a cycle here, right? We're talking about a single component. Yeah, I think people don't understand cycles that well, but I don't blame you because we haven't really done very many cycles. So that's fine. We'll get to it. The one that I had for last class, this was just a copy of what I had in the exam. So I was hoping that it would be 100%. Let's try to get 100% on my next survey, okay? Everybody get it right. This is more like what I got when we were in the class together, something like this kind of distribution, which you should have because all you have to do is look at the exam. Somebody still said heat, work, energy, and heat and work. Yeah, so these are really wrong. I don't know, people just guessing just to throw something in there. I don't know, but certainly if you thought about it, you would get the right answer. With 52 people did that and got internal energy as the right answer. So internal energy plus flow work term. H equals U plus P times V. Okay? Really important to know. Definitely will be an important factor for the final exam that you'll have to understand. Okay, let's move on to new material. We're ready to go to new material. So let's see. Here we go, new material. Get rid of my notes and get rid of everything else here. And there we go. Okay, vapor power systems. We're actually entering the portion of the class that I like the best, which is thermodynamic cycles. Because thermodynamic cycles are useful things that we deal with in everyday life, even if we don't know it. For instance, vapor power cycles, if we're ever use electricity, which most of us do, we're using the product of a vapor power cycle. So that's pretty cool. We can talk a little bit about that today, and hopefully we'll get through the ideal Rankine cycle today and do an example by the time we're done with class today. and then you'll have a sense of what ideal the vapor power cycle is all about. Okay, and in it are processes that you've seen before already. This is the beautiful thing. It's all just additive from what we've already learned. All the processes that you'll see and all of the stuff, there's no, from here on out, there's essentially no like new material. This is just, it's like recipe. You built the rest, you got all the ingredients. Cycles are just like the recipes. So what we've done before is like the ingredients and making side dishes and stuff, and now we're putting them all together into a meal. That's how it works. Okay, that's what cycles are all about. Okay, what are we going to do? So learning outcomes are explain the basic principles of vapor power plants, vapor power cycles or vapor power plants, develop and analyze thermodynamic models of vapor power plants using Rankine cycle and its modifications. So the Rankine cycle is named after Rankine. Okay, there's nothing special about that. And its modifications including sketching, schematic, and accompanying TS diagram. Notice that there's only a TS diagram that we use to describe this cycle. It's perfectly sufficient. Applying mass, energy, and entropy balances for the basic processes, and determining cycle performance, thermal efficiency, net power output, and mass flow rates for all the components in the cycle. And then the last thing is we're going to describe the effects of varying key parameters on Rankine cycle performance. I hope to get to the point where we discuss modifications to the Rankine cycle to make it more efficient. We'll either get to that or we won't. I don't know. I'm giving myself 2 lectures to get through this. So we will see what we get to. Okay, so let's get into it. Oops. Okay, so introducing power generation. So to meet our national needs, there are challenges related to declining recoverable supplies of non-renewable energy resources, which we know. Actually, it doesn't seem like we'd have non-renewable resources right now when we have oil that yesterday went below zero, negative. People were paying somebody to take oil from them, right? Crazy times, as I said, crazy times. Effects of global climate change and other environmental and human health and safety issues. That certainly is a concern and is increasingly a concern. But I guess in the past couple of weeks, a lot of people have shown that the emissions and pollution have gone down considerably. Maybe all we need to do is just have remote classes and remote everything, and then we can curb climate change. Rapidly decreasing demand for increasing demand for power owing to increased population. That is an issue. Going to keep going. Today, we're heavily dependent on coal, natural gas, nuclear, all of which are non-renewable. I think I have an issue actually. This is from the book, this text, and calling nuclear non-renewable is a little, yeah. I mean, I guess the main point, it's not renewable in the sense that uranium is depleting and you can't get it back, but certainly emits no CO2. So, I mean, I think we could have a whole class debating that. Okay, so let's move on. Okay, while coal, natural gas, and nuclear will continue to play roles in years ahead, contributions from wind, solar, and other renewable sources are expected to increase. That is certainly true. We're seeing Iowa, the state just to our south, is one of the leaders in wind energy. I think we could be similar if we had the right policies in place. Solar, actually wind is solar because solar is what generates the thermal gradients are what causes the wind in the first place. So it's kind of all solar. If we're going to do anything renewable, it's got to be from the sun. The nuclear power generation in the sky. Okay, let's go on. Thermodynamic cycles are fundamental. Several power plants that employ renewable and non-renewable sources, right? So this is the modern take on it. It used to be that vapor power cycles were described as coal power plants because that's what we used to have. When I was a kid, that's all we had. But now we have all sorts of vapor power cycles. Gas turbine systems, internal combustion engines are also studied in chapters 8 and 9. But vapor power cycles, which work as a cycle where we turn a working fluid, into a vapor and then back and condense it again. So that's why we call it vapor power cycles, because we're working with the phase change. The phase change enables high efficiency, which we will see and understand in this chapter. Okay, the components of 4 alternative power plants configurations are, and there's a figure I think in the book, figure 4.1 in the book if you want to go and check it out. Fossil fueled power plants, those would be like the coal plants. the ones that I worked at when I was a student in Pittsburgh. Pressurized water nuclear vapor power plants. So even nuclear power plants operate on the same cycle as the Rankine cycle. Concentrating solar thermal power plants. So power plants that use solar concentrators, essentially big mirrors that focus on a small area and boil water or boil some sort of fluid that changes phase. Or geothermal vapor power plants, so using hot water essentially from the earth, or using, like if you live in Iceland, they have a lot of geothermal activity, so they have a lot of volcanic activity that you can tap. So there's all sorts of those types of systems. They all operate in a similar kind of power cycle, which we will learn about today. So in fossil fuel power plants, the energy required originates in the combustion of the fuel. That's what it says. Okay. Now, in this case, this is a very classic vapor power cycle arrangement from burning some sort of fossil fuel. You can see here on the left, fossil fuel is given here, air. So this stuff is combusting in a burner. But if you see the dotted line kind of separates from that, for this class, we don't care about this. This is just where the emissions come from. We're really more focused on B. And B is the thermodynamic cycle, okay? That's the thermodynamic cycle we're going to study. We're not going to study this other stuff. Electric generation, that's how we take work from the turbine, and we make electricity out of it. We actually have a pump in here we need to put some work into, as we'll find out it's minuscule compared to how much power you get out. You have a pump for water in a cooling tower. This is the modern environmentally friendly version of this. When I worked as a power plant engineer as an intern in Pittsburgh, I won't tell you what year, but we used the river as the cooling tower. So essentially, instead of this like cooling tower that would vaporize and come down and make a pump and go around and around in a circle, and you'd make up water, which goes in there, which is right here. You would use the river, and this thing would be the river, and you would take cold water from the river and you'd dump warm water back into the river downstream. Now, this has all sorts of environmental challenges. I mean, it's not that you're contaminating the water, you're just heating it, right? Which causes some effects on wildlife and algae buildup and all sorts of other things. But typically, this isn't done anymore. But a lot of places it is, even along the Mississippi River. They have plants that will take the water in, put them through a condenser, and then spit them back out. All right, we're more focused on the B, which is the cycle in between. You're going to see a couple more examples here. So here's another one. This is a nuclear power plant. You're going to see the same elements here, though. I wish I could draw on my PowerPoint slide with my fancy pen. I wish I could just draw on it, but I can't. Maybe I can do it with. Well, no, I'm not in presentation mode. So, oh well. You're just going to see my cursor here, okay? So this is like the boiler here. This is the control rods where they heat up the water and all sorts of stuff. Let's see. We're taking the warm water. So here's the cooling tower again. So the cycle is here. Actually, the cycle is boiler, feed water pump, condenser, turbine. See, there it is right there. I wish I could make a dotted line around it. Let's see. Let's just do it. Let's insert a shape. I'm going to put a dotted line around that. We'll go ahead and make it dotted in a minute. So this is our system. This is what we're interested in here. And we don't want it we don't know fill, and we want to make this a dotted line because I actually took points off people in their exams who did not put dashed lines around their system. Okay, you have to do it. It seems silly, and you might think it's silly and stupid, but it's not. It's what we need to do. Okay, so if you didn't put a dotted line around your thermodynamic system in your exam, I took off a point. Okay, so do it. Just do it. I don't care whether you don't like it or not. All right, so here we go. This is our control volume. Okay. Technically, you would label a control volume, but I don't want to do that because I don't want to run out of time. But this is the system that we're talking about, okay? Same system in nuclear power plant. Same system here. So I'll do it again. Actually, better thing to do is just to copy it. Let's go back. Yeah, so I'm just going to take this guy. I'm going to copy it. I'm going to put it in the next slide because we're going to identify the system here. So here's a molten salt or oil. Then you're receiving heat. Goes into this as our boiler, essentially. And so then if I define our thermodynamic system for the power cycle, it's here. So there's the there's the stuff, the same thing, right? So this is the same system. There it is again. So we got a pump, a boiler, a turbine, a condenser, and some cooling tower or river or whatever you have. Okay. Here you're receiving heat from the sun to heat a molten salt, which then has a higher temperature than the boiling point of water, hopefully quite a bit, because we'll learn hotter you go, the better in terms of efficiency. And then you've got a renewable power cycle. So that's pretty cool. Next one is here. Let's do the same thing. So here is my box. Same thing here. This one's a geothermal. As I said, if you're in Iceland or this becomes even more attractive because you have like molten lava down underneath, and you can use that really high temperature organic substance. So if you want to just use like hot water down below, you can use like another kind of organic, what they call organic Rankine cycle, which is like a fluid that boils at a much lower temperature. So you can use organic Rankine cycle. You can use, actually it can be non-organic too. It can be ammonia or something like that. You can put in the cycle that boils at a really low temperature, and then you can use that in your power cycle. So anyway, so here's our power cycle here. If I can just use my box, and you can see there's a power cycle. Okay, good. So as I said, just to reiterate, we're interested in the thing in the dotted in the dashed box, right? This other stuff is cool, and it shows you how we can use this power cycle, and how it's applicable in different applications to make energy. Or we're not making energy. Sorry, that's the thermodynamic faux pas. You never make energy, right? Never say I create energy. I mean, a thermodynamics professor should never say that. So bad. We transfer energy from one form to the other, right? So we're producing electricity from heat in this case. Okay, so here we go. Back to the fossil power plant. It doesn't matter. We have the four things. You have the boiler, but really we're interested in B, right? So water is the working fluid usually. So this is the heat transfer coming from the what's in the red box is coming from the combustion and heating up the stuff. B is the power cycle. This is what we're going to be studying. C is the electric generator. This is where we get electricity from, and there's some switch gear and transformers and stuff that are off here to the right that are not showing. And then this one right here is the water rejection, which I've already talked about, which is either cooling tower or river or lake or something. Okay, but we're really interested in this Rankine cycle. This is what's called the Rankine cycle, right? So the different components of the Rankine cycle, as we will see, they go around this loop, and we have these 4 different processes. So there's 4 different pieces to the Rankine cycle that we're going to study. Okay, let's do a little cycle review, right? So you know about cycles. We've talked about them from an abstract perspective. Remember in my cycle example in the midterm, I said there was a turbine inside the cycle. Guess what? There's a turbine inside this cycle, right? We're not drawing it in here because we'd have to really do it really tiny to put that in there. But look, there's a hot body, which is the boiler. The gases from the boiler, the hot combustion products or molten salt or whatever it is. And it transfers heat into the heat exchanger, right? In the case of a power plant, it's usually a bunch of coiled tubing. Anyways, and that steam is going in there, and then you make some work from the turbine, and then you have heat rejection, which is the lake or the river or whatever it is, or the cooling tower. And there's your T in, your Q in, and your Q out in your work cycle. And as we know, the work cycle, the cyclic integral of work is equal to the cyclic integral of heat for a cycle. And so we have work cycle equals Q in minus Q out, so it doesn't violate the Kelvin-Planck statement. And the thermal efficiency is given by work over Q, which most of you got in the exam, so I think you got this one down. So first law of efficiency, you got it, okay? Good, so this is a cycle like any other. And so these are just this is the caveats, right? So the second law of thermodynamics requires that the thermal efficiency be less than 100%. Most of today's vapor power plants have thermal efficiencies ranging about 40%. If we think about it, the Carnot efficiency, we'll get into that a little bit. We don't quite reach the Carnot limit with these, but we can get close by doing lots of bottoming cycles and other things. We can get close to the Carnot limit, which is near the 60% range. Thermal efficiency tends to increase as the average temperature, which energy is added by heat transfer. So as I said, hotter stuff is always better, especially hotter stuff with respect to the temperature of the boiling point of the fluid. Improved thermodynamic performance of power cycles is measured by increased thermal efficiency. I think this is obvious. If you have less irreversibilities, of course, the thermal efficiency is increasing. And the extent of the power cycle performance is limited and by constraints imposed by thermodynamics and economics. Of course, you can have a very, very, very super efficient system, but if it costs millions of dollars more money, then probably power companies like Xcel Energy or whoever are not going to install it. Okay? But we're not going to be talking about economics in this class. But you can imagine that more money you spend on it, there's a trade-off between money and efficiency, right? And at some point they wash out. Okay, Rankine cycle. So here it is. Here are the 4 components that we just talked about. There are 4 principal control volumes, including these components. So we could put my dotted line back out here, make my dotted line around everything, right? And so actually, when I say there are 4, the slide says there are 4 control volumes, actually there's 5, right? You can make the overall system a control volume as well. So the overall system can be a control volume, which is what we do when we sort of have Q in and Q out. I wish they Q out is sort of like this, right? So Q out, it's more like that, right? So Q out, don't worry about what's coming in and out of the control volume in terms of fluids. So if I can make this really close to the boundary of the turbine, that'd be good. There we go, something like that, right? So you have Q out, you have Q in, you got the turbine work, you get the pump work. So you only have the works and heats kind of going through this system, which is what I'm talking about. Of course, there's probably heat loss as well, but we're not going to talk about that. So we have these 4 components: the turbine, the condenser, the pump, and the boiler. Now, we can put your 1, 2, 3, 4 wherever you want on this thing, so long as you label it on your diagram, which you have to make, and on the TS diagram, which you also have to make whenever you do one of these cycles, okay? The 2 key things you have to remember is that we need to have a diagram of the cycle. I need to know that you know what the components are, and I need to know that you know where everything falls on a TS or PV diagram. In the case of a vapor power cycle, the TS diagram is the only one we need, okay? So anyways, then we have all the conventions, the sign conventions, but in this case, they're taking it as the positive direction for the arrows. Okay, Rankine cycle. The process of Rankine cycle is vapor expands through the turbine developing work. We know that already, we've done that. Vapor condenses to liquid through the heat transfer of the cooling water. Heat transfer, we've done that. Liquid is pumped to the boiler requiring work input. So it's a pump, we've done that too, right? That's actually a really simple pump because it's incompressible. So we know that incompressible stuff is really easy to deal with, right? So we just pump it from one place to the other. Okay, and liquid. So process 4 to 1 is liquid is heated to saturation and evaporated through the boiler in the boiler through heat transfer by the energy source. All right, so this all sounds like just words until we actually look at the TS diagram, but we'll do that in a minute. Engineering model. Each component is analyzed as a control volume at steady state. The turbine and the pump operate adiabatically. Generally, we assume that they operate adiabatically. They may not, but we take that up in terms of efficiencies, which I'll discuss when we get into non-ideal cycles. But especially for the ideal cycle, we assume that they operate adiabatically. Kinetic and potential energy changes are ignored throughout the entire cycle, so don't worry about it in the cycle analysis at all. 0. Okay. All right, those are the assumptions. Now, turbine. So we know, applying the mass and energy balances for the turbine, so m dot equals m dot throughout the entire thing. So m dot 1 equals m dot 2 equals m dot 3, blah, 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 all the way through the cycle is equal to m dot, the mass flow. So the power, big W dot, over m dot equals H1 minus H2, so the power of the turbine. So that would be actually little w, right? Little w is equal to H1 minus H2. So that's a really simple thing because we're eliminated. The first law just kind of eliminates all the potential kinetic energy effects, and they're steady state, so there's no dE dt. Condenser, you have Q out over M equals H2 minus H3, so that's really simple. Pump, same deal. So these things are all adiabatic, right? Except for the condenser and the boiler. They don't have extra heat loss terms, so you don't have to account for those. So boiler is Qn over M dot equals H1 minus H4. So super easy stuff, right? This is not rocket science. And the cycles, to analyze the cycles is really quite simple. Now, there's going to be steam qualities and stuff in here, so it gets a little uglier than this, but it's really not difficult. Okay, performance parameters. So thermal efficiency equals work over Q, which is total work of the cycle, so which is turbine work minus the pump work. So these are little w's, little wt minus little wp over little q in, and so that equals all the enthalpy terms. So you can probably simplify this, right? Because there's 1, 2, 3, and 4 here, and 1 and 4 here. Probably can simplify it, but it's just as easy just to know what those h's are and calculate the efficiency that way. There's one more thing. So we haven't talked about this because this is really specific to cycles. What's called the back work ratio. So the back work ratio is the amount of work you have to put back in order to run the cycle, right? So there's always a little bit of work. That's why we always said that the work you put in the efficiency term was what's called net work. So there's always some work that you got to put back in order to compress or pump or whatever. In this case, the back work ratio equals the pump work over the turbine work. But as I said, since it's incompressible and we're pumping liquid, the power requirements, this H3 minus H4, is really negligible compared to the overall power that you get out of the turbine. And so generally, as it says here, the power required by the pump is generally less than 1%. So usually the back work ratio for a Rankine cycle is less than 1%. So it's not very costly in terms of your energy requirements. You pay for it all with the heat that you put into the boiler. Okay, provided states 1 through 4 are fixed, meaning that a steady state, right? They're not changing. The developed equations can be applied to determine the performance of simple power plants adhering to the Rankine cycle. Since these equations are developed from mass and energy balances, they apply equally and irreversibilities are present and for idealized performance. So this is an important point. So these equations here apply whether it's reversible or not reversible. It doesn't matter, right? Because this is first law. This is all first law stuff. So if the only thing that would be if this was like not adiabatic, like if it was a non-adiabatic turbine, then you'd have to put a Q term in here. Okay, the only terms that you'd have to add in here, maybe you have some heat loss here, heat loss here. So you could put in some extra heat loss terms probably, but they're certainly applying to the ideal Rankine cycle. Okay, so what is the ideal Rankine cycle? The ideal Rankine cycle provides a simple kind of scenario to study the aspects of vapor power plant performance. The ideal cycle adheres to certain assumptions, and those are that the frictional pressure drops are absent during flows to the compressor and boiler. The processes occur at constant pressure. So there's no pressure drop through the heat exchanger. Now, a typical boiler in a power plant has almost like a mile of tubing that the water flows through as it boils. They're like coils. They go up through the firebox. So this is definitely not true. There's always pressure drop in those lines, but ideally we say no pressure drop. So the pressure stays the same through the boiler and through the condenser. Flows through the turbine and pump occur adiabatically and without irreversibility. Thus, these processes are isentropic, meaning that we don't have excess heat loss and they're reversible. No friction or anything going on, weird mixing or turbulence or anything happening inside there, which is also, of course, not true. But we assume that they're isentropic, means that we can analyze them really easily using second law. Okay, so this is the key diagram that I get to here. The ideal Rankine cycle consists of 4 processes, and here they are, and they correspond to those components. So as I said, 1 to 2 we said was a turbine. 1 to 2, so it's an isentropic turbine. So 1 to 2 goes down here like this. It can happen inside the vapor dome, or it can happen outside the vapor dome. We're going to talk about the relative advantage of having it inside or outside the vapor dome. Meaning, like if we boil, we add what's called a superheater and superheat the steam up beyond the saturated vapor point. But assume now we have this goes to 1, 2, and then this is where we expand, and we expand down to some low pressure, and then we actually have to reclaim the water and make it into water, and this is where the condenser falls out. This is where the river is down here, where the Q out, and then this one's 3 to 4, meaning that we're pumping. You see how tiny that is? So TS is like really tiny. TDS is 0, but like the work here is really minuscule. And then 4 to 1 rather, is when we're going from heat transfer. This is the boiler. So you run up the constant pressure line, right? Because we said it's constant pressure, and you hit A, which is the saturated liquid point, and then you boil all the way till you hit saturated vapor. and then you go back down to the turbine again. Okay, pretty straightforward process, and we're going to talk a little bit about it. How are we doing? 35 minutes. Okay, then I'm going to have time for my example problem, which is great. So since the ideal Rankine cycle involves internally reversible processes, we can look at chapter 6 as a way to solve this thing. And therefore, when we said we had reversible work from a pump or turbine, we said we could use VDP, right? Only when we have reversible processes. So when we have a reversible pump, it's VDP, integral VDP. So this becomes easy because V is constant we assume V is constant. Because it's incompressible, right? So it's not compressing. You don't have a change in density. The density is the same, 1,000 kilograms per meter cubed. So that's, 0.001 meter cube per kilogram. And then that's pretty much what it is for water. So this becomes really easy. The pump is like the easiest part to analyze, especially for the ideal Rankine cycle. Okay. And we can use a second liner, entropy balance, areas under the process in the TS diagram can be interpreted as heat transfer. So obviously if you have heat transfer going into two processes, right, because the pump and the turbine are adiabatic, you got processes going into the boiler, which is the dark spot all the way down, the hatched line, and then what's coming down here, 2 to 3 from the condenser is in the hatched line only. And you can see that the subtraction between those two is what's in the shaded area, and the shaded area represents the total heat, the net heat, Q out minus Q in of the cycle. Okay? Hopefully you understand that. It makes sense to you. All right, so that's the ideal Rankine cycle, not the ideal superheated Rankine cycle, which is shown as 1', 2'. All right, so this takes me to my example, which is the last thing we're going to do today. And I'm going to do an example of an ideal Rankine cycle so that you can do a homework problem on this. So let me get here, and then we can do it. So water is the ideal process for an ideal Rankine cycle. What I'm gonna do here? Maybe I can't really pass it from one thing to the other. Well, I might be able to. Just draw it out. I was thinking about ways to be lazy and actually not draw the cycle, but I'm going to draw the cycle. I'm going to do it. Okay, here we go. All right, so, oops, I don't know the red. I was doing something else with the red before on the. Okay, here we go. So known, we have an ideal Rankine cycle. Okay, we have with water as a working fluid, which is pretty typical. Condenser pressure is 8 kilopascals, and we have a pressure. So we have the two pressures essentially. Remember, they're constant pressure, so there's operating between two pressures. Determine the heat transfer kilojoules per kilogram of steam flowing for the working fluid. Oh my gosh, really? We've just given you two pieces of information, and you can determine the heat transfer of the steam flowing for the ideal Rankine cycle. Isn't that amazing? Okay, so known, we have to find. Determine the heat transfer for the working fluid passing through the boiler and condenser. So we want to find Q in and Q out. Q condenser, Q boiler. Okay? Those are the things we need to find. All right. Per kilogram of steam. Okay. So we are going to just run through the analysis here. Assumptions. All right, so first I'm going to say that 1 is an ideal Rankine cycle. And 2, we're going to say that we have steady state. And 3, so ideal Rankine cycle takes into a lot of things into account. Delta P equals 0. And then it assumes that all the assumptions. So I'm just going to leave a steady state ideal Rankine cycle, okay? Because this assumes everything. So isentropic this and isentropic that. So once we're doing these cycles, if you say ideal Rankine cycle, I know what that is. And then you don't need to write down every single assumption that you have for that thing. You know it's steady state. You know it's ideal Rankine cycle. You just we'll just move from there, okay? So for the sake of time. Okay, so we need two things. When we do cycles, we need two items. The first thing we need is we need a drawing of the actual deal, so the cycle itself. So we're going to just have the boiler, call this the boiler. We have a turbine, which is the thing that makes the work. So there's little w. I'm just going to label it little w. So we're going to just go in there, and we're going to come out here, and then we're going to go to a condenser, from which we have Q, what do we call it? We'll call it Q out. And here we have Q in, right? And here we have and then we have a pump, which I'm going to use the universal symbol for pump. And then it's important to put arrows to know which direction the cycle is going, because if you go the other way, you're going to have a different kind of cycle. So let's keep it, let's just erase this and just make sure you know what this is. There's a turbine, okay? We don't have to draw our overall system yet because, so this is work pump, this is the work turbine, okay? Because we don't know what we're going to analyze first, but we know this is our overall thermodynamic system. The other thing we have to make is a nice TS diagram. Notice I said nice. Okay, we want it to be nice. We want a nice TS diagram. Make a nice vapor dome. We want to have our two pressures. So there's one pressure at 11. We say one is at 11 megapascals and the other is at 8 kilopascals. So down here. So 8 kilopascals. So this is 11,000 and this is 8. Right? Wow, huge difference in pressure. Big difference, right? 8 kilopascals is way below atmosphere. Actually, in real life, they do pull a vacuum on the turbine sucks down below the atmospheric pressure. So they actually have a vacuum in the condenser. Okay, so ideal Rankine cycle means we're going from here. Oh, let's put our numbers on. So we had 1, 2, 3, and 4. So this is 1 then. I'm going to say ideal Rankine cycle goes here, 1, 2. Always good to put arrows here too. Put arrows on your cycle diagram. 3 is here after the condenser, and then we have pump to 4, and then 1 back to 1 again. So it looks like this. Okay, pretty straightforward. That's all you got to do for TS diagram. If you've got data, you can plop it in there. But in this case, we only have the two pressures. But really, that's all we need, because all we need is, since we have an ideal Rankine cycle, we know exactly where these points are, because we know 1 is at the saturated vapor and we know 3 is at the saturated liquid. So that's pretty straightforward. So, so if we do our analysis, let's just kind of fix each of the principal states. So, and you remember what I mean by fix, right? That means that we find all the conditions, so we know exactly what the thermodynamic states are. Okay, so here we are. How much time do I got? Okay, I'm going to get through this. Okay, so we know state 1, we know that is at, did you say this is 11 bar? Yeah, it's 11 bar. So state 1, we know P1 equals 11 bar equals P sat. So we'll know what the temperature is, but it doesn't really matter. So H1 equals Hg at 11 bar. And this one equals 2705.6 kilojoules per kilogram. And then we might need to know S as well, because we need to find the corresponding S down below, because that's the only one that has a quality associated with it. So S1 is equal to Sg at 11 bar, and that is equal to 5.5527 kilojoules per kilogram K. Now I know you guys were rushed during the exam and you had a hard time putting units in. I didn't take points off for that, but I really prefer that if you can, wherever possible, put units in for your stuff. That way I know that you know what you're talking about, and if you made a mistake, I can easily track it. Okay, so I just wanted to point that out. Okay, so state 2. So we say no state 2 that P2 is equals 0.08 bar, and it's also saturated. It's a saturated pressure. So S2 is equal to S1 by the second law, because we know for an isentropic turbine, second law. So isentropic turbine little s2 equal to little s1. So then we know this is equal to 5.5527. And we know so that S2 is equal to SF plus X2 plus SFG. Oops, X2 times SFG at 0.08 bar, which you can look up in the table, and we get X2 is equal to, you guys can look this up hopefully, 0.6496. Okay, so I'm not going to write out all that stuff, but you get this for your quality. So now we're at 60% quality, which is, and my diagram's not quite that good, but this doesn't look quite 60%. It looks more like 80%, but that's okay. It's 65% quality. And then H2 then is equal to HF plus X2 HFG, which then if you plug in the numbers here, you get 1734.84 kilojoules per kilogram. Of course, quality has no units. Okay, and then we have, so we fixed state 2. So state 3, sometimes it's useful to make a table. You can make a table, and that's really helpful when I'm actually creating an exam or homework. You just make it, up here you could just make a table for fixing the states, like here, just make a table, but I'm not doing that. But you could do that. It makes things look a little more organized if you like to be organized. State 3, so we know that P3 is also 0.08 bar, PSAT, but we also know that we're at the saturated liquid line. So that means that we're H3 equals HF at 0.08 bar, and this is equal to 173.88 kilojoules per kilogram, and that we also have S3, so S3 equals SF at 0.08 bar, and that equals, what is it? Actually, we don't need to S because we're going to do VDP. So let's get rid of this. So we're going to do VDP. So V3 is equal to VF at 0.8 bar. Oh my goodness. Okay, 0.08 bar is equal to 1.0084 times 10 to the negative 3, so meter cubed per kilogram. Okay, so then we have that, and then so then state 4, we only need two intensive properties, right, to fix the state. So we fixed that state with 2. We can find S if we wanted, but we don't need it, as I said. So H4 is equal to 173. So H4 we can find. So if we look here at where state 4 is, state 4 is somewhere up here. Oops, don't do that. But state 4 is somewhere up here in the liquid. So it's right here. It's somewhere in the liquid phase, subcooled liquid. We'll just say subcooled. Definitely, you want to pump subcooled liquid, right? You don't want to pump. A vapor. That would be bad. So let's just say we're going to use the first law. We'll know that H4 equals H3 plus work. 3, 4, or work of the pump. We'll just call it work of the pump. Okay, and where work of the pump equals VDP, H3 plus V P4 minus P3, because work of the pump is equal to V integral V dP. And V is constant because it's incompressible, which makes this super easy. So we'll just call this V3, because V3 equals V4. Incompressible. Okay, so it's incompressible, we know that. And then, yeah, we're almost done. So H4 then is equal to, we can just find this because we know the pressure. State 4, subcritical liquid P4 equals, what is it? It's 11 bar. At 11 bar. Okay, so H4 then becomes, it's pretty easy to find. It becomes 184.96 kilojoules per kilogram when you use this equation here. Okay, and you use the steam tables, of course. And then, so then all we have to do is find what Q in. So Q in is equal to, so Q in is a positive, right? So Q in is equal to H1 minus H4. That's in the boiler. And this is equal to, which we have already, 2705.6 minus 184.96. And this ends up being 2520.64 kilojoules per kilogram. So that's Q in. Q out is equal to H2 minus H3, but it's negative. It's H3 minus H2, but it's negative because we use it a positive sign convention, so that it's H2 minus H3, which is a little confusing. I'm sorry about that, but H2 minus H3 is equal to 1734.84. So we already have these numbers that we solved when we fixed the states, 173.88. And this ends up being 1560.96 kilojoules per kilogram. And that's the answer for the second part. Now, if we wanted to calculate the efficiency, which is work net, so it's work turbine minus work pump over Q in, which is equal to, if we just solve it, it's actually 1 minus Q out over Q in, if we use the first law, which we've done before. This is not new, okay? I hope I don't scare anybody there, but I just making this leap here. This is not new. Just say not new. Okay. And then, so anyways, we do this, then we have Q out, which is 1561 essentially, and this is 2521. And this ends up being 38.1%. So it sort of validates their, power plant efficiency. Actually, an actual Rankine cycle would have less than that, but this is a simplified system, and we're not superheating. And what we're going to find out next lecture is if you superheat, if you go up here, if you bring up 1' up here, and then bring this back down, you're in much better shape in terms of efficiency. You can push it up higher. But yeah, so that's it. So that's the Rankine cycle, the ideal Rankine cycle. So today we've kind of gone through the whole deal, and hopefully that was useful for you guys and you understand it. I'll give you a chance to practice an ideal Rankine cycle for your homework. It may be only a 10-pointer, but I don't know. We'll see. It might just be one problem. Okay, with that, thank you, and I'll see you Friday.